Good afternoon, everyone. We are going to get started in just a second. I'm excited to meet with you today to talk about making sense of phenomenon. And I am recording the session so you can view it whenever you get a moment. And if there's any questions that you have that I don't go over or I miss, please feel free to email me at the end. You'll see my email address, so you can email me any of those questions that you do have. So we're going to go ahead and get started with our presentation today. So today is all about 3D science and making sense of phenomenon. And we know that phenomena is very important. It's part of those high yield, high engagement instructional strategies that our district has prioritized this year to address unfinished learning. So if you look here, we have those unfinished learning priorities or commitments that our chief academic officer has set forth for us this year. So this making sense of phenomena and making sure we utilize phenomenon with our students is going to be hitting on high impact instructional strategies that you can use in the classroom. Along with that, our balanced science instruction priorities for this school year. We're going to be hitting on teachers will use phenomenon to drive instruction in the classroom, and teachers will move instruction from 1 dimension to 3 dimensions. So as we go through today, what a phenomenon is and how we can utilize those authentically and effectively in our 3-dimensional science classrooms, I want you to think about the overall picture, and that is this balanced instruction document that we have for science. So we know that 3-dimensional science has 3 dimensions. So we have our disciplinary core ideas, dimension 2 being those science and engineering practices, and dimension 3, which is those cross-cutting concepts that cut across the curriculum and helps students make connections with the other dimensions. We're going to be looking at phenomena today, which is basically the anchoring piece of the 3-dimensional science approach. If you look at our balanced instruction document, you can see that our 3 dimensions are embedded within this document. And this is how we promote and we teach students here science in Cobb. So let's get going and let's talk about how we can make sense of phenomena and give our students something authentic to develop their disciplinary core ideas around. So what are natural phenomenon? So a lot of the information that I'm sharing with you today has come from 2 different books, and I have them at the end of the presentation, but the author of that being Brett Molding, who was integral in developing the next generation science standards and the new K-12 science framework that lays out how we can use 3-dimensional science teaching. And they say that natural phenomenon are things that occur in our universe, and students have to use their science knowledge to explain or predict what is happening. So they're going to observe it, and we're not going to immediately tell them the answer, and they're not going to know what the immediate underlying cause is. And we want them to wonder why something happens, right, with a phenomenon. It's something that is observable and it occurs in the universe, and we want them to question why something is happening. So the why is the cause, and what happens is actually the phenomenon or the effect. So I want you to think about that today as we move through the presentation. So let's look at this example. This is just a quick example to kind of get you thinking about a phenomenon. So here's my example, and I have a picture here. You could throw this picture up on your RecordX panel and just have students look at it. But our question here, our phenomenon here, is why does the sun appear to rise in the east each morning? Now, of course, I'm not going to give students the answer to this. I'm actually going to have them do an investigation or a student performance to figure this out, but I wanted to let you see an example right away. So the phenomenon or the effect is the sun appearing over the horizon, right? And the knowledge we want our students to get to, because we're not going to tell them, we're going to I want to say facilitate their learning in order for them to figure out what is happening. But this is happening. The cause of the sun appearing to move from east to west is actually the way the earth sits on its axis and it's rotating from west to east. And so that makes the sun appear to rise in the east and move towards the west. But this is an example of a phenomenon that you could use to anchor a lesson or a unit with your students. So let's dig a little bit deeper into phenomenons. So here's some just quick examples that I thought of because we want to provide our students with authentic and relevant and real world examples of phenomena that they might encounter in their daily lives. And we want to connect that with the disciplinary core idea or the content, the science content that you're teaching. So here's just some examples. Some birds sing in the morning and others sing at night. What's causing that to happen? The bees make a buzzing sound when they fly, but moths do not. Not all grass is the same color of green. So these are just some more examples of authentic phenomena that you can use to anchor a lesson or a unit. And these are things that probably have happened in the students' lives or maybe their daily lives that they've never really understood or figured out on their own, but it made them wonder. We want to spark their curiosity. We want them to wonder why something happens. All right, so making sense of phenomena. You'll hear this a lot as we do trainings for the rest of the year. But really, what that means is students are connecting the explanations for phenomena to their existing schema. And that schema is the core ideas, the cross cutting concepts, and maybe even, like it says here, similar phenomena and personal experiences. But what we want them to do, and I have bolded that, that's the third quote right here. We want students to engage in making sense of phenomena by developing questions, collecting and analyzing data, generating and utilizing evidence, and developing models to support explanations and solutions. Boy, do those sound familiar. What do those remind you of? They make students make sense of phenomena by basically engaging in those science and engineering practices to figure out what is going on. That's the do part of science, what scientists and engineers do. And that is those science and engineering practices. So basically, we're going to present a phenomenon to our students. We're going to allow them to engage in making sense of that phenomena by utilizing those science and engineering practices. So let's look at that a little bit closer. All right, so you have your frameworks and you're looking at your standards that you need to teach. And now we have prioritized standards and supporting standards. You're looking at those and you're thinking of a phenomenon to introduce that way. Introduce that content with. How can you introduce a phenomenon? Well, there's lots of different ways. We need to make sure that it captures student interest and it's not boring to them. Nobody wants to sit in class and, have a teacher present something that's supposed to be wow and make you wonder what's happening. And it's not interesting. It should be presented in a way that causes students to develop their own questions. That's the biggest part about utilizing anchoring phenomena is the questioning that comes along with it. We want students to think about what they already know about the content and what they still might need to know in order to figure out what's happening. And we want to present them as observations. We definitely don't want them presented as explanations or learning targets or essential questions. So let's look at this example on the right-hand side, effective ways to introduce phenomena. And this is an example of an Earth-Moon system. So the teacher is teaching about the Earth-Moon system and how they correlate and interrelate. And these are three examples of effective ways. So you could tell a story to describe the phenomenon. And this is the example that they used. We were camping at the beach. The moon appeared to be a reddish color when it first came up. A few hours later, the moon was much higher in the sky and looked white. You might even have students that raise their hand and say, oh, wait, I've seen that before. This is what happened when I was camping or something like that. Perfect way to introduce a phenomenon. You could even have students interacting with it. So here you could make and record observations of the moon over a month and report their observations. And video clips, a time-lapse video clips and students summarize what they observe are all effective ways to introduce the phenomenon to your students. I've even used photographs, like actual photographs that I have found either in a science text or on the web. You could even play a, not a time-lapse video clip, but just a regular video clip. You might find something else on YouTube that you could utilize as well, but you want it to be very highly engaging for the students. So remember, phenomena are observations, events, facts that can be investigated and explained using science. I think that's the number one thing that teachers need to understand and remember when they are planning three-dimensional science lessons where they're going to be utilizing and anchoring phenomena. Number two, we want the phenomena to cause students to wonder and motivate them to ask questions. Once you introduce the phenomena to students and you're getting ready for them to do a science performance or a student science performance, we want that guiding question board to come first. We want all of those questions written down about what they're wondering or what they know and what evidence we can find. And we're going to add to it as we move through the student science performances. Number three, phenomena lead students to plan and carry out investigations. I'm going to show you an example of that in just a moment. We don't want phenomena to be questions, explanations, concepts, theories, or activities. And I think a lot of times science teachers who are moving from one-dimensional to three-dimensional science learning, they think of these really cool activities for the students to do that connect to the phenomenon, but then really it's just an activity and students aren't really developing that science knowledge that we want them to based on the activity that they're doing. All right, so let's look at some examples of phenomenons and non-examples that go together. And maybe this will help to help you to understand with that last little number 4. Remember, we don't want it to be an explanation, an essential question. We don't want it to be an activity. So here's some examples. So let's start at the bottom. So my shadow changes position throughout the day. That's the phenomenon. We know that in elementary school, I know this is middle and high, but just so you know the progression. In elementary school, they study how shadows move through a fixed object's shadow can move through time throughout the day. So same thing, my shadow changes position throughout the day. Here is an activity that a teacher planned. This is just an example. I haven't seen this, but I know a lot of teachers that do this activity using a tetherball pole, chalk, a clock, track, record changes in the position from the pole to use as evidence. That's well and fine, but that's your evidence. That would be the investigation that you do. The phenomena would be that my shadow changes. Well, why does that happen? You would do this activity as an investigation to figure out why this motion is happening or the position is changing. Some, but not all squirrels can fly from tree to tree. So that would be a phenomenon, right? A non-phenomena would be an explanation of that. Flying squirrels inherit characteristics from their parents. If you threw that up on the board with a picture of a squirrel, okay, then the kids already know why squirrels can fly from tree to tree, but we want them to figure that out through an investigation or some research and then construct that explanation. So these are just some more. I saw mushrooms growing in a circle in my backyard. That's a phenomenon. And then a classification or a fact would be mushrooms are a member of the fungi kingdom. So you can see here the difference between a phenomenon and a non-phenomenon. All right, so let's take a look at an example. So we looked at just a very generic one earlier about the why the sun appears to arise east to west. We're going to look at one now and look at how students could engage with a series of performance prompts after the fact. So I have a picture of a guy taking or exhaling on a very cold day, and to go along with the phenomena that sometimes on a very cold day, you can see your breath. Now, I know, unless they've been living under a rock, I think every student would have some kind of background knowledge and actually experience this for themselves. But there's a lot of systems working together to actually make that happen. So you would show this picture and then the statement, sometimes on a very cold day, you can see your breath. So to make sense of this phenomenon, we want students to engage in a series of performance prompts. Now, I'm going to show you how we can do that with the science and engineering practices and the cross-cutting concept. We're not going to go through every single one of these, but I wanted you to see what it could look like. All right, so the student performance is, with this phenomenon, is plan and carry out an investigation to gather evidence that supports an explanation for causes of your breath being visible when you exhale on a very cold day. Now, this statement is completely different from the phenomenon. This is the student performance prompt or a student science performance, what you want them to do. So they're not only engaging in planning and carry out an investigation, they're gathering evidence, and we want that evidence to support their explanation. And they're going to figure out what's causing that. And that gets to that disciplinary core idea. So you can see how we're interconnecting or interweaving all three dimensions with this student science performance based on the anchoring phenomenon on sometimes on a cold day, you can see your breath. So if we want students to ask questions, they might ask, what causes a change in the appearance of my breath on a cold day, and investigate that, or coming up with more questions. If we want them to construct explanations, they're going to use information from the investigation and their prior knowledge to construct that explanation. If we want them to, like here, develop a series of investigations to support with evidence, first they need to determine how they're going to gather evidence. We're going to facilitate that learning. We're not going to guide them. We're going to facilitate. We're going to listen to their ideas, because they might think, like it says here, maybe I can investigate breathing into a baggie in the house and releasing it outside to see if it changes. Or you can use air collected on a warm day and collected on a cold day, observe how it changes at various temperatures. So they're coming up with the ideas on their own, and you're facilitating that. Let's look at some more of our SCPs. Developing a model. Students could develop a model to show the relationships between matter and energy and the systems involved, and the representing relationships between states of matter. If we're constructing explanations and developing models, they're making their explanations supported by evidence. And here's a quick example of what a student explanation could be. The water we exhale is gas. When it moves into the cold air, the water quickly loses enough energy to change into tiny droplets of liquid water that reflect light. So we see our breath as a white cloud. Super simple, only a couple sentences, but the fact that they planned and carry out an investigation to gather that evidence to support their explanation, and they developed a model to do that, and then constructed an explanation based on that model, is three-dimensional science learning. So I just wanted to show you how you could take an authentic phenomenon and then prompt it with a student science performance like this, where you give them what they're supposed to do. You want them to plan and carry out an investigation to help them come up with an explanation. But here they're engaged in those science and engineering practices in order to help them understand and connect with the cross-cutting concepts, which you see here in green. And then that gets them to the explanation or the cause of why something is happening. So when students are engaged in making sense of phenomenon, they use multiple practices, those cross-cutting concepts, and the core ideas. The student performances, like we just went over, create opportunity for students to gather that information, reason the relationship to the phenomenon, and communicate explanations supported by evidence that they gathered during the investigation, which is huge, which is actually the hardest thing for teachers to actually wrap their head around is, okay, we can pick out an effective and an interesting phenomenon, but what do they do then? What can I have my students doing then to actually get to the reason or what is happening, what is causing this phenomenon to happen. And you do that through student science performances. And we're going to have a training later on in the year, probably next quarter, that kind of goes more into depth. So let's think about the phenomenon we just had. Sometimes on a cold day, you can see your breath. So multiple core ideas are needed to make sense of this simple phenomenon, right? Here are the simple core ideas that the students had to use in order to make sense of this. They had to know that matter is made of particles and that they can move from one system to another. They had to know that energy flows from the system with more heat energy to the system with less heat energy. Energy is involved with matter changes, and those cycles and energy flows among living and non-living there's different matter cycles between living and non-living parts of systems. So really, when you think about it, one simple phenomenon could create so many different synapses in our student and have them connecting all of those core ideas. And the way they do that is through the cross-cutting concepts. So if we think about these core ideas, let's think about those cross-cutting concepts that kind of go throughout. Well, we know systems is one because that word is actually in the core ideas. Structure and function, energy, let's see what else, stability and change, cause and effect, right? All of those can be connected with the core content that the students just worked through. So let's recap phenomenon. So making sense of phenomena refers to students connecting the explanations for a phenomenon to their core ideas, cross-cutting concepts, and personal experiences. They construct meaning and knowledge that becomes more comprehensive and sophisticated over time as you give them more rigorous and relevant phenomenon to work through. And we know that our students engage in making sense of phenomena by engaging in those science and engineering practices like developing questions, collecting and analyzing data, generating evidence, developing models. So this is really to kind of get you thinking and stepping in the direction of providing your students with effective and authentic phenomena to support your three-dimensional science teaching. So hopefully this helped kind of explain that a little bit and what the difference between, an explanation or a concept or a theory is related to an authentic and effective phenomenon. The resources that I used today, I used engaging students in science investigations using the GRC, and the GRC stands for gathering, reasoning, and communicating. And then teaching science is phenomenal, which came out in 2018 by Roger Bybee and Brett Molding, who, as I mentioned earlier, Brett Molding is one of the authors of the NGSS and the new framework for science teaching that really uses the gather, reasoning, communicating. And he came up with student science performances and all that really awesome stuff. So if you have any questions or you would like more information about how to implement effective phenomena in your classroom with your science content, please do not hesitate to reach out to Christian, Callie, or myself. And also hit us up on Twitter as well if you're doing anything cool in your classroom.